All right.
Right, so we'll start our last talk of the afternoon, and it's Carola-Bibiane Schönlieb, and she will talk about model-based learning in imaging.
Thanks a lot, Malcolm, and thanks a lot, Anders, for inviting me. So Michael mentioned quite a lot machine learning in his presentation. I'm not sure, because I just came, were there any machine learning talks so far? In fact, anyone talking about machine learning and inverse problems? No. Okay, so that's actually quite surprising because it seems it's omnipresent in whatever you do nowadays. So what I will do in this presentation is to discuss approaches which are trying to bring together more of our classical inverse problems approaches in variational regularization in particular, and ideas from machine learning to find particular instances of approaches which are trying to bring the two together. And so the idea is both to think about how machine learning can help variational regularization to be more adaptive towards data, but also how can variational regularization help us maybe to influence what we are doing within machine learning. And that will be a perspective that is very much colored by my personal path in this area. It will start out with so-called bi-level optimization approaches that I've started working on by now 4 years ago when I met a colleague of mine from the University of Quito in Ecuador, who is specialist in optimal control. And so everything started basically with PD constrained optimization. And then I will go to some more recent approaches, not just by myself, but also by other people who are going in the direction of bringing ideas from variational methods into neural networks. Okay, so let's start with the more, I would say, modest approach of trying to understand how we can make variational regularization maybe more adaptive. And so I start out with just a brief introduction to variational regularization, motivating a little bit why we might want to think about adapting what we are doing in regularization to data. I'll then discuss bi-level optimization approaches plus some of recent ideas in neural networks, how to integrate variational regularization in training these networks, and then I'll stop. Okay, so first of all, just to set the scene, in what I'm going to describe, G are always my measurements. They're connected to the quantity U that I want to reconstruct, which in my case is mostly an image or a sequence of images. They're connected to U via a forward operator T, and there is also always little n there, which stands for random corruptions in the data. And so what I will mainly focus on in this presentation is this variational regularization approach, where I'm trying to find an approximate solution to this equation by minimizing an energy with a data discrepancy term, which tells you, which quantifies the forward model against the measurements, and a regularization term R that should regularize your inversion. And then I have a little parameter here that I call alpha that balances the two guys against each other. Okay, so this is just to set the scene. Now, Michael had the Shep-Logan phantom, or you didn't have it, but you alluded to the Shep-Logan phantom in your presentation. And actually, the first example I will give is with the Shep-Logan phantom, but with a similar idea in mind to say that not the same type of regularization always works. But I'll still start out with that, which is the idea of using a type of regularization that assumes that the U I would like to reconstruct from G has a sparse representation in some basis. And one very well by now standard and very well very established approach to impose sparsity is by using the total variation as a regularization. And so this is an example simulating what happens in magnetic resonance tomography, where my forward model are samples of the Fourier transform, and the quantity U that I would like to reconstruct is an image. And so why this idea of sparsity is working so well if you just compare it to what I call here the zero filling solution, which is just basically setting all the Fourier coefficients that I don't know to zero and then invert the Fourier transform. Why this works so much better is because this is the Chape-Logan phantom. The total variation sparsity models the assumption that my image can be very well approximated by homogeneous constant areas where nothing is happening and just a few discontinuities, which are the places where the gradient of U is non-zero. And so is this always realistic? Well, if you go to real-world applications, actually, surprisingly enough, very often this works very well. So this is an example of a dynamic MRI application, where what you see here is a tube filled with water, and then in this tube there is a smaller tube where a tracer is injected. And what our colleagues here from chemical engineering are interested in is the dynamics of this tracer. So monitoring this tracer over time. And so this is a 4D MRI example where what you see here is just one slice through the tube and how it evolves over time. And what you see here is one time snapshot of this tube rotating around. And so this is a reconstruction from 20% line samples in K-space. And what you see here looks pretty well with a TV-type regularization approach. If you compare that again with the zero filling solution, everyone will say, wow, this is great. I mean, we should always do TV, right? This is wonderful, and this is not even, if you think about this, this is not even something that looks remotely like the Chape-Logan phantom does. Well, okay, so then you go on and look, go back from, return from your real measurements to some simpler examples, some simulated examples that you construct, and that again look very simple, but they also show where the total variation is likely to fail, namely when this piecewise constancy assumption is not fulfilled. And this is just setting the operator T to be the identity, so just a denoising example, where you see that in these areas where the intensity function is linearly decreasing or increasing, the total variation is actually doing a pretty bad job. And this is not just because of the total variation, but it's because of this combination between L2 discrepancy and total variation. But nevertheless, this just should make the point that not the same type of variational model is always appropriate. So then you think what to do, and many people have thought about what one should do in this case. And then you could do something, again, like we have seen in Michael's case, not to take the total variation of the distributional derivative, but the total variation of the distributional Hessian. And then you can resolve the linearly decreasing intensity areas very well, but you're blurring out the edges. And then again, you can go back to your drawing board and think about how to get the best of both worlds. And one example of combining first and second order sparsity, if I may call it like this, is to use something like the total generalized variation here of second order, where you're basically decomposing your U into parts where a first order sparsity is more appropriate and in parts where second order sparsity is more appropriate. Okay, so all of this is fine. The question is, of course, always which type of sparsity representation, which type of regularization should you choose? And even if you think, well, actually, maybe we could stop here and this is really the guide that we should always use, even here, in this case of the total generalized variation, you see here these parameters alpha 1 and alpha 2, they're actually quite crucial and need to be tuned to get a result that looks like this.
Are they constant through the whole image, or are they?
So they are constant. Yes. Yes. And then you could go even further and think, well, okay, sparsity is one particular type of regularization or prior that I could impose on U. So we have seen also smoothness is another prior that is very often actually more appropriate than sparsity. But then there are even, there are tons of different prior assumptions that you could put into variational reconstruction approaches. Here in this case, this is an example where you have, again, a dynamic imaging scenario where you might want to put some physical model that you have about the motion that is happening into the reconstruction. And what you see here is just one example where the forward operator that I now called K is just a projection on a couple of pixels, and this even changes over time, and this is the reconstruction that you can get from such an approach. So anyway, so just the point to make is we always have to think, when we get a new problem that we have to solve, we have to think what type of variational regularization approach, for instance, we want to use to solve it. And that's not, the regularization is not the only thing that is a degree of freedom in these variational models. Very often, if you look at this line here, very often also the type of distribution of your data influences, for instance, which type of discrepancy term you want to choose. In magnetic resonance tomography, very often people use an L2 discrepancy because they come with the assumption that normally distributed white noise is a good approximation to what is happening there. In positron emission tomography, for instance, Poisson distributed noise is present, and so people are using type of Kullback-Leibler divergence to quantify the forward model against the data. And then in photography, for instance, very often because of failures in the mechanism of your camera, you might have impulse noise or salt and pepper noise or things like this, and then again a different data discrepancy should be used. And then the last thing is, of course, not only choosing the regularization and choosing the discrepancy, but then also how much should I regularize. And there are, of course, different types of approaches how much you should regularize, but they all rely, again, on understanding a bit more about the type of data that you want to process. So in inverse problems, very often we use things like the discrepancy principle, for instance, if I have a good estimate on the noise level in the data. So now I would like to take a different point of view onto this, which is the point of view that I've mentioned at the beginning of phrasing our quest for a good variational model in terms of a bilevel optimization scheme. And so here the idea is, mimicked here by this set of different images, the idea is if I look enough at examples that I would want, that I desire my variational model to spit out, if I look at enough images that I would like my variational model to have as a solution, maybe I can find, and I parameterize this variational model sufficiently, maybe I can learn the good parameterization that gives me solutions which are close to these examples by optimizing over a particular loss. And this loss I need to define. Okay? This loss, you can think, should somehow quantify how far my solutions here are from the examples I have in this training set. Okay, so let's start with learning of variational models. And I should say, so I mentioned at the beginning everything started with PDE constrained optimization, and that really started with Juan Carlos, who is at the University of Quito. And then a couple of people have joined along the way, Martin Benning and Matthias Erhardt, who are in Cambridge, and Matthias is actually sitting here in the back. Tuomo Valkonen, who is at the University of Liverpool. Ferdia, who is a PhD student of mine, and Luca Calatroni, who is at École Polytechnique. Okay, so just to recap what I've said before, what we somehow want to do is, if I have a set of training pairs of actual measurements that I take, that are my FKs, and corresponding ground truth images UK, which could be ground truth or at least close enough to the truth such that I would like to desire to compute them. If I'm starting out with a set of training pairs, what I now would like to investigate is the idea of starting out with saying I would like to compute based on FK, I would like to compute reconstructions UK bar as solutions of a variational model, and I would like to choose this variational model in a way such that the solutions UK bar are close to my desired examples that are in the training set. So this is the idea. Very simple idea. And this is just a conceptual slide. I'm not going to do all of this that I'm saying here. I'll give you some examples of doing this. So here you could think about minimizing over the type of regularization that you want to choose, maybe also the type of discrepancy of how you want to quantify your measurements against the forward model. You might also want to learn how much you want to regularize. And maybe, and this is very much going back to ideas from optimal model design, maybe you even want to think about how optimally to acquire your measurements. And many people have thought about this, and I'm sure this is not an exhaustive list, but I'm just giving you a few examples, so I hope no one is offended. And I'm only talking about bi-level optimization here, so learning with bi-level optimization. I'm not trying to capture the whole picture of what people are doing in learning at the moment. So I've mentioned, so let me just pick out a few things. I've mentioned optimal design. And here there is some very early work by Leo Horash, Tenorio, and Eldad Haber, starting in 2003. There are some guys actually, and this is something we found, was one of the first works we found when we started off thinking about this in terms of PDE constrained optimization, which have looked at the type of reaction diffusion equation and parameterized this reaction diffusion equation in a way, and then tried to learn the good reaction diffusion equation to smooth an image. So a bit based on this PDE model of Perona and Malik. And then, so we started in 2013 thinking about this, And at the same time, also Tom Pock and Karl Kunisch started to think about this idea of learning variational models via bilevel optimization. And a couple of people then also looked at this in the last years. So let me mention in particular Michael Hintermüller. So I'm presenting you all of this in a supervised framework where I say I have my training set and then I learn a good variational model. Michael has an interesting approach for learning adaptive TV. So in this case, the alpha would be spatially dependent by using as a loss function statistics, noise statistics that he runs over the image. Okay, so Michael has very much emphasized this idea of doing things in the continuum. And so what we really started out with, also as I said, I'm really coming from a PDE background, is phrasing this bilevel optimization scheme of learning variational regularization approaches in function space. Okay, and that looks like this. So I said before the first slide was conceptual. This is now one example of what you can do, where you can both prove something and solve it numerically. So here we're looking at one particular type of parameterization of both the regularization term and the data discrepancy terms. And so here this looks much more complicated, in fact, but it's much easier to capture mathematically. So what we have here as a regularization is a linear combination, or this could also be an informal convolution of different types of total variation regularizations. The total variation regularization of an operator AJ applied to U. So that captures TV, that captures TV2, that captures TGV. And then the type of discrepancy term we are again phrasing as a linear combination of different types of discrepancy terms. Again, this can also be an informal convolution. And what we are now learning is not the AJs and the phi i's directly, but we are feeding those into the variational approach, and what we are learning are the weights in front of those. Okay? And those could be either scalar, and the examples I'm going to show you are all for scalar alpha and lambda, but they could also be spatially dependent. It depends on the type of application you have in mind. What's my loss function? What I'm optimizing for? And so again, naively, very naively, my initial excitement about doing something like this is to get a kind of objective point of view of what an optimal variational model is. But that's of course naive, because you are choosing the loss function. You're choosing with respect to what you want to optimize this variational model. And so here we tried one particular types of losses. We tried a least squares loss, comparing your solution of the variational model with your example in a least squares sense, which very much mimics what people are doing when they are showing you their best results in terms of the peak signal to noise ratio. So this would correspond to maximizing the peak signal to noise ratio. And then we also looked at not just not quantifying your optimality just in terms of the intensity, so not just in terms of the U itself, but also in terms of the gradient of U, or the gradient of V. Okay, and if you do this over a training set, you're of course looking for an optimal solution that is an average optimal over this training set. Okay, so let me skip this actually, and let me go to this slide. So since I don't have too much time, I will only tell you briefly what one can prove about this bi-level optimization model, and also what the challenges are in proving anything here. So the first thing is, if I briefly go back to this, the first thing is what you somehow need to avoid is, if you want to prove well-postness of this, if you want to prove at least existence of this, of these optimal parameters, what you need to pay attention to is that the moment alpha, lambda and alpha are either 0 or tending to infinity, you're losing compactness here in the lower level problem. Because you're either losing the regularization, well, that's actually the main point. You are actually, you might end up losing the regularization. And so kind of also reassuringly, what we could prove is that automatically the optimal parameter will lie in the interior between 0 and infinity, under appropriate assumptions on your training set. If your training set, if your FKs are already perfect, then of course this wouldn't hold true. But the moment you're starting with imperfect FKs, the regularized solution is always better than just doing least squares. The other thing is, if you look at the existence, so this is just about the existence. This doesn't tell you anything yet about how you can turn that into a numerical scheme. And so what we did here for the numerics is we used the quasi-Newton method, so something that relies on computing the gradient of your cost functional with respect to the parameters. And so for that, we had to give up a little bit on the non-smoothness here. And we could prove, and what we did, just to tell you very briefly, what we did is we smoothed the total variation here, make it differentiable, and we also shifted this variational approach, which is set in a Banach space, into a Hilbert space by adding an elliptic regularization to this lower level problem. So in this setting, we can again prove existence, and then also, and this is crucial, continuity of the optimal solution for the smooth problem. Derive an optimality system that we will then use in our numerics to get the gradient of the solution map. And then, of course, always when you smooth, you want to make a connection to the original problem. We could also show that solutions of this smooth problem will converge to the non-smooth problem, at least in Hilbert space. We couldn't give up the Hilbert space structure, so the elliptic regularization was always present. Okay. Now, numerically, as I said, we use the quasi-Newton method. We combined that if the training set was very large, we combined it with an idea of Bird and co-authors of dynamically sampling the constraints, so not solving for all the constraints in every iteration, but just for a subset of those. And the crucial thing here, which brings the numerics close to the analysis, is that because we have an optimality system, we can just read off the gradient of the cost functional from the adjoint equation. So that was crucial here. Okay, a few results. Again, starting very modestly, what I'm showing you here is a parameterization of the variational model which is just one parameter. It's just a regularization parameter in front of TV. So I fix the total variation as a regularization term, and I fix an L2 discrepancy for my data fidelity term. I look for the inverse problem here is actually just a denoising problem, so T is the identity. And as a training set, we've just chosen the Berkeley database, the Berkeley image database as a training set. And so we're just optimizing over one parameter, and the thing we wanted to understand is how robust is this parameter for this application of denoising, and it's pretty robust. So this is just showing you the cross-validation of learning and testing on 100 images in each of these training and validation sets. Is it optimal? Well, it looks like if it would be optimal. This shows you the cost function over which we are optimizing against the regularization parameter alpha. And what you see here is that this is our optimal computed one. And as I said, there is this relation to the signal to noise ratio, that this is maximized. But is it really optimal? And so, I mean, this looks convex, in fact, right? But is this convex? And I'm showing you here something that that Pan Liu and Irene Fonseca showed me recently, which is a constructed example, but a very simple example where you immediately see that there is not even quasi-convexity of this problem, even with just one parameter. So this is a constructed example where we are using explicit solutions of total variation regularization in a paper by Strong and Chen in the 90s, where my noisy signal that I'm starting out with, okay, this is one-dimensional. My noisy signal I'm starting out with is very simple, doesn't look really noisy, but let's assume this is my noisy signal. And this is the corresponding solution of the total variation regularization approach for one choice of parameter. And here you see the cost function plotted against different choices of parameters, and you see it's not convex. So this is very simple, right? And it doesn't look, I mean, maybe you're not that scared by this non-convexity, but I think this is very representative of any kind of machine learning approaches. And here we just have one parameter. It's a very simple type of machine learning approach, if you wish. And already here, things like this are showing up. What about TGV? As I said at the beginning, in TGV, the crucial choice is the ratio between how much you weight the first and how much you weight the second order sparsity. And again, here we did this cross-validation from before, and it's pretty stable with respect to that. So you can learn the good ratio between alpha and beta. And here you see the result, and actually, here you see one example, one pair of original ground truth and noisy image that is put into the training set. And what I'm showing here, this is just to show you what the effect of the different types of optimality criteria are. So here, this is my L2 cost, least squares quantification between the denoised image and the original one. And what you see here is the optimal denoised image, but optimal with respect to this gradient cost that I've also introduced before. And actually this beamer is, I think, quite good, because I think you can actually really see a difference. And, well, it depends what you like better. But so there is still a degree of freedom, so you could think about now learning the cost function as well, but well, I'm not going there. I think this just very much resembles that, even in terms of what we have done for years and years of designing variational models and evaluating them, there is always the question of how you evaluate them. What is your quality measure that you use in order to say one is better than the other? And often our eyeball norm we can't really formalize well. So, okay, let me skip this. This is just showing you the energy landscape for TGV for these two parameters, for two different cost functions and for two different images. And now the funny thing is, if you are able to optimize this variational regularization approach for different types of regularizers, you are also able to evaluate different types of regularizations against each other. And so again, this was a toy example where what we did was we tested the performance of TV versus TGV versus ICTV, which I haven't mentioned, but this is another form of combining first and second order sparsity with each other, again on the Berkeley database for different noise levels, and then we checked for each one of those which one got the optimal result. Optimal with respect to the cost function, that in this case here is our gradient-based cost function, and the color shows you which one was the best. And so you can do this for various noise levels, and then somehow what this result gave is this ordering. So TV was the worst one, then TGV, and then ICTV. Now again, this ordering is very artificial. I'm just pointing towards some of the things that are always a bit critical, not just in this very simple type of learning, but in machine learning in general. I've trained this on this Berkeley database. This is a database of images of a particular resolution, and okay, I've chosen 3 different noise levels, but still, this is an ordering that holds for this particular type of resolution, and if you go to another resolution, maybe your answer will be different. You can not just learn the type of regularization, but as I said, you could also try to understand what type of discrepancy terms should you choose, and maybe you can do funny things like finding an optimal decomposition of an application where you have mixed noise. So again, this is here constructed, this is my original one, and this is my noisy image. Again, the operator T here is the identity, where the noise here is composed by Gaussian noise and impulse noise. And what you can do then, if you phrase your discrepancy term as an infimal convolution between, again here I've regularized a little bit, but let's think conceptually here. Just this is an L1 discrepancy for approximating the impulse noise component, and this is the L2 discrepancy for the Gaussian noise component. You can also use this to do this decompositions into the clean image or the denoised image, your impulse noise component and your Gaussian noise component. And of course, because of the bias the total variation introduces, this is not pure Gaussian noise. There is some structure in there as well. So now Anders has left, but actually Anders would like that, because we also looked into this question of learning the best acquisition. How should you best acquire the data? And here in particular we looked at magnetic resonance tomography, where what we are optimizing over here is the sampling pattern that you should choose. Which is modeled here just as a diagonal matrix with either entries 0 or 1. And again, what we are optimizing the sampling pattern for is that the solution of a total variation type regularized problem is closest to whatever ground truth I'm providing it with. So now I will very quickly go over that the sampling pattern matters. I think every one of us knows. This is just showing you for the same amount of sampling, the different types of regularization that you get if you sample with different distributions. And so what we were interested in was whether a very simple bi-level optimization approach like we have started out with, if that could capture that in any way. And this is a starting example just to show you the effect on something that we can somehow understand and interpret easily. This is my ground truth image, very simple, even simpler than the Cheb-Logan phantom. And what I'm doing here is this is the Fourier transform or the logarithm of the modulus of the Fourier coefficients. We put some noise on them, and then these are this is the learned sampling pattern. And something I haven't said, but I should have said, is that of course, the optimal sampling pattern would be if you fully sample, but we are steering how much you sample by putting here a sparsity constraint on the sampling pattern, and depending on how you choose beta, you're allowed to sample more or less. So this is optimizing the sampling pattern, assuming you have a particular budget. Okay, and this is what you get. This is the learned sampling pattern, and here I'm just plotting this against the largest Fourier coefficients, the same amount that this was optimized for. This is this weird number because it relates to the beta. Okay, and this is the comparison between the two. So looks reasonable. And if you zoom in, you can see that the learned sampling pattern seems to pick up better the higher frequencies, and actually it's going out there a little bit. So it seems to do something a bit more clever than the largest Fourier coefficients are doing. This is a bit more complicated example where here in red you see the largest Fourier coefficients. In yellow you see the learned sampling pattern, and in white you see where both of them where they both are the same. And this is the ground truth image, and this is the best reconstruction, again TV, so you will, this is just what TV is doing, with the largest Fourier coefficients, and this is with the learned sampling pattern. And what you can see here, I mean the reconstruction is in general not very good, but what you can see here is that the learned sampling pattern again seems to bring out more the smaller scale details in the original ground truth image. Okay, and then in the last 3 minutes, I've promised you that I will tell you a little bit about how you could bring this a bit closer to what neural networks are doing. And so one thing I would like to start out with is the work of Tom Pock, as I said, started also with Karl Kunisch in 2013. Where the parametrization is already much richer to what I've said. I've started out with this combination between different types of total variation regularization. But here, what Tom is doing is giving much more freedom to how the regularizer could look like. And so how he's phrasing this is that he's modeling the regularization as this kind of fields of experts model, where the smoothing operator, if you wish, is called here KK. So it's a linear combination between different types of smoothing, and this is a convolution. So you're learning the entries of this convolutional kernel. So these are the parameters, the free parameters. And then you also want to learn which type of norm, again, maybe, or which type of metric you should use to model the regularization. This is here parameterized in terms of radial basis functions. And so you're learning here the rho k's and the k k's. And again, in this bi-level optimization framework with an L2 loss. And so these are the things that you get out. These are the KKs, the typical KKs that you get out of this. And these are the type of nonlinearities that you get, the rho Ks. And what is interesting here, that at the very beginning, what appears is some something that almost looks like a derivative. Actually, you know, some backward difference or something like that. And then if you compare that, so what he did here was he compared that with, so this is again just image denoising, and he compared that with different state-of-the-art image denoising methods. And what you see here, I mean, these approaches are really modeled for image denoising. What he's doing is quite generic, so just to say that. But still, it kind of beats some of these state-of-the-art denoising approaches. So that's kind of nice. And then we're still not with neural networks, because neural networks, when you send your input into your neural network and wait for your output, you're not solving a variational model in between. You are applying different types of operations, a finite number of operations to your input till you get the output. And so what he's doing here is trying to bring a little bit together this idea of variational models and this finite number of steps that you do in a network by what he calls the variational network, where what he's now learning is what each layer, what the operations in each layer should be. Again, in terms of linear operators kk and nonlinearities rho k, and these now can change in every step. The only thing that is fixed here is the number of layers, if you wish, that you have, which is here capital T. And then he can really beat everything that was out there, at least I think 1 or 2 years ago. Okay, one other idea, and Michael might know about this. I'm just starting with this approach of Ozan and Jonas, because what I will do maybe in 1 minute is just to say what we started out based on their approach, is to say I'm still, this is again a tomography framework. I'm still phrasing my tomographic reconstruction in terms of some iterative scheme, a learned gradient scheme, but each step in my gradient scheme is given by a deep neural network, where the deep neural network in this case is not just fed with the tomographic measurements, but is also fed with a gradient of the discrepancy term. So this is where the information of the forward operation comes in, of the forward operator comes in. And which is not here, but it could be fed with other things. It could also be fed with some type of regularization that you might want to initially impose. And so again, let me mention that this is connected to what Michael has done with his UNet architecture for starting with a filtered back projection, getting a regularized reconstruction by sending that through a UNet architecture. So what we're thinking about doing here is to using this learned iterative approach, not just to reconstruct an image, but to reconstruct an image for a purpose. And the purpose, what I'm very briefly going to show you, is classification. And reconstruct the image already having in mind that and at the end you want to classify it. And so this is joint work with Ozan, Jonas, and Sebastian Lunz, who is one of my PhD students. So in this case, what we're interested in, and it's just this first line here, we want to recover probabilities of looking at the MNIST database, which just consists of images of the digits 0 to 9. We want to recover probabilities that these images are 0, 1, 2, or blah, 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 9, starting from sinogram data, from tomographic measurements, which in this case are measurements just taking 5 angles of these images over 25 lines. And these images are very small, they're 28 by 28, so you would think that might be a reasonable thing to start with. And so the idea here is, and let's just only focus on this line. The idea here is that we want to train, so we want to solve this with a deep neural network, with this learned iterative approach, but we want to already do the reconstruction, having in mind that we want to classify in the end, which means that you are already reconstructing by optimizing over the cross entropy that evaluates your classification at the other end. So I have to be a bit quick here, but let me just show you very briefly what this means. So these are typical examples of starting with these 5 angles and 25 lines plus noise, what a filtered back projection result would give you. Okay? And if you look at those, I don't know for how many of those you can say which digit this is. So let's go through them bit by bit. So if you look at this, just the classification based on the filtered back projection would give you is that this is a 9. If you do this together in a joint framework, it also tells you it's a 9, and it also gives you not just a 9, but it also gives you the reconstructed image, and it is actually a 9. When you look at this, what is it? Any guesses? Okay, let's see. So the deeply learned classifier says it's a 4. It's very sure about it. The task-based reconstruction plus classification also tells you it's a 4. It's even surer. Well, it's not that sure actually about it, but and it gives you this task-based reconstruction as well. Well, could be a 4, and this is actually really a 4. Now, what about this one? So the classification based on this thinks it's an 8, and it's very, very, very sure about it. And actually, the joint, the task-based reconstruction plus classification thinks it's a 4. This is the task-based reconstruction, and this is the true thing. So I think I'll stop here, and I'll just say the last thing I wanted to say is that many people now in inverse problems are trying to somehow understand how we can take advantage of what is happening in deep learning. And not just taking advantage of what is happening in deep learning, but maybe using some ideas in variational regularization to also understand what is happening there. So not just using what they're doing, but also to complement them with some of the things that we know from variational regularization theory. But then also coming from a physical inverse problems background, also understanding how, without throwing away everything that we have done over the last years in terms of physical modeling, how this is still relevant in a learning context. And here I've just put up a table of, positive and maybe negative points about both of these paths that you could take. And I think what is now arising is to find models that are somewhere in between the two. And there are many things that I've not mentioned. I've just given you a few examples of of regimes where people are thinking about bringing those two together, trying to have maybe a table with 3 columns at one point where everything is green. Not sure, but so this is somehow the idea. Can we bring those two worlds together, the modeling and the learning? And I will stop now, Malcolm. Sorry. by just saying that I think why we like variational regularization models so much is because we can prove things about them. We have guarantees. We get solutions that we can prove things about, that have stability criterions, and that we can derive error estimates for. On the other hand, variational models are quite rigid because what we put in there is what we get out. And so the idea of learning is is somehow very encouraging in a sense, because learning seems to do very well in adapting to different types of data. So somehow can we learn structured but adaptive models with guarantees? And there are lots of things to do, but I think I should really stop now. So thank you.
Time for one question.
Non-convexity seems to be a huge problem.
Yes. I mean, yes, so on the one hand, yes. On the other hand, I mean, when you think about deep learning, why we are worried about the non-convexity is because we somehow want to get the global optimal solution, right? But if you think about this training, with this learning over a training set, you are anyway only capturing part of the whole distribution that you might want to approximate. And so not optimizing this globally might be okay.
There's a sort of an argument with deep learning that you've got really big parameter spaces, and so there's not just one good minimum, but millions.
A lot, and which are equally good. And
presumably, if we've got a small parameter space, so like you showed the one-dimensional case, that might actually be quite bad.
Yeah. And actually, that's also interesting, because what we at one point also did was to look at a model which is a total variation type regularization model with 3 parameters, where you're trying to understand how best to regularize in each dimension in a dynamic imaging scenario. And there, actually, the local minima really didn't look good. Whereas when you talk to people like Tom, who are also solving this, but for thousands of parameters, the local solutions are fine. Yeah. So the parameterization, I think, is really crucial to have a rich enough parameterization to still be happy with local minimization schemes to solve these learning approaches. Yeah.